A kind of basic skill is to be able to do these icebox problems. So I'm just going to go through two of these icebox problems and give you a chance to see how they work, and you can try them again on all the different worksheets that we're doing. One of the ideas is when there's an X, is it small enough to ignore? And we'll look at how to tell. And then there's a shortcut that we can use with these icebox problems. First problem, calculate the pH of a 0.2 molar solution of HF. So we should recognize that that's a weak acid, and since it's a weak acid, then it is going to break up into H plus and F minus. Now our icebox, the initial values across the top row, the change, and the equilibrium values across the bottom row. We're given here that this is a 0.2 molar solution. We're not saying anything about H and F, so we know those starting points are 0. And we are going to write our Ka expression, which will be the concentration of H plus times the concentration of F minus over the concentration of HF. And we have a value for that, and that is 6.3 times 10 to the negative 4. Now, we run out of numbers, so we're going to say, let's say X, HF breaks up, so we're going to form X of the H plus and F minus. So at equilibrium, we see that these two values would be X, and this would be 0.200 minus X. Now, because this is the weak acid, we're saying we start with a lot of HF, but that some of that HF is going to break up, and the amount that breaks up is so small that you really can't see any difference in the HF value we started with. So what we're actually saying is X is much smaller than 0.2, and therefore not subtracting this X won't make that big of a difference. So when we substitute in over here, we're going to say we have X times X over 0.2. Now officially as 0.2 minus X, but we're making the assumption that that X is small enough to ignore. And we have a nice little way to tell how small does it have to be. You look at this number, your initial concentration, and you look at this number, your K value, and if this number here is much smaller, and we say 10 to the 2 to 10 to the 3 times smaller, then it is X is small enough to ignore. So we see our initial value, this is 10 to the minus 1, 10 to the minus 4, okay, that's 10 to the 3 difference. X is definitely small enough to ignore. So now we just substitute in, so we have X squared over 0.2 is equal to 6.3 times 10 to the negative 4. And if we go back and calculate, we're going to have X squared equals 1.26 times 10 to the negative 4. So we don't want X, we don't want X squared, we want X. So we'll take the square root of both sides. The square root of 10 to the minus 4 is 10 to the minus 2. And the square root of 1.26 is 1.12. So this is our X. X is our H plus. So our H plus concentration is 1.12 times 10 to the minus 2 molar. And we're going to take the log plus minus of that, and we're going to get a value for a pH of 1.95. Now, since this is actually 3 significant figures, we'd actually be 1.951. Now, this kind of problem, okay, really standard icebox problem, where we start off with an initial value, 0 and 0, minus X plus X plus X, and we get a value here, X and X. We're going to say that's a really standard sort of problem. And when we get down to this point here, then we can see what's happening is our X is equal to the square root of this number times this number. That's where we got the 1.26 times 10 to the minus 4. So we're going to come back and do this again as a shortcut. Let's try another problem. Okay, here we have NH3. And in this case, we have to put in some water because NH3 is a proton acceptor, and we need a molecule for it to accept a proton from. So it becomes NH4 plus and OH minus. Our initial value is 0.2. Again, we don't care about these values. 0 and 0 minus x plus x plus x. And this is 0.200 minus x, x, and x. Comparing this number with this number, we see, okay, x is small enough to ignore. So we're going to work down here at the bottom, and we're going to say this time our Kb is equal to the concentration of NH4 plus times the concentration of OH minus over the concentration of NH3, and substituting in our equilibrium values, we can see we're going to have x squared over 0.200, which officially is 0.200 minus x, but we're assuming the x is small enough to ignore, equals 1.8 times 10 to the negative 5. So, by multiplying, we see x squared is equal to, equals 3.6 times 10 to the negative 6. And to get x, we take the square root of both sides. And we get 1.897 times 10 to the negative 3. It's a little sloppy, sorry about that. Now, that's our x value. We can see our x value in this case is the OH minus concentration. So we're going to take the log of that number, and that turns out to be 2.72, which is our POH, and subtract from 14. So our final answer, I'll change colors, is 11.27. And in fact, because this is a 3 significant figure, this is 2 significant figures. Okay, this is our good value. So our pH is 11.27. Now, let's go back and look at our shortcut. The initial one, we said the x value, since we do this over and over and over, we can see that the x value is equal to, okay, this number times the Ka, take the square root of that. So let's just use that as our shortcut. So the x value, x, which in this case is going to be our H plus concentration, is equal to the square root of 0.2 times 6.3 times 10 to the negative 4. Now we've already done this problem. It's a little messy, but we can find out that when we multiply, that's 1.26 times 10 to the negative 4. So we're getting the square root of that, which equals 1.12 times 10 to the negative 2, and taking the negative log of that value gives us our pH. So the negative log 1.95, and since this is only 2 significant figures, this is only going to have 2 significant figures, so that will be our value. In the same way, if we go back to our second problem, and we can see that x, which in this case is going to be our OH minus concentration, and we see that by looking at our ice box. Let's go back and look at it. So x is going to be the OH minus concentration, that's important, equals the square root of our initial concentration times the K, which equals 3.6 times 10 to the negative 6, and the square root of that is 1.897 times 10 to the negative 3. Now when we take the negative log of this value, we're going to get 2.72, and that we have to realize is our POH. So our pH, we subtract from 14, and we get 11.28, which is our answer. Now if I went more significant figures, I think I got 11.27 last time. But this is the shortcut, So when we see that we have a standard icebox problem and we're doing, say, multiple choice question, then we can jump and do the shortcut. Do keep track of whether that X, however, is H plus or OH minus, and if you're not sure, go back and do the icebox. Practice this.